Hello students. So this is our second lecture for chapter 1 Electrostatics of 12th class. Now in the previous lecture we have studied how we can charge by conduction and by induction. Let us see the few differences between the two methods of charging. Now in the first method, if we bring a charged glass rod, let us say positively charged glass rod, in contact with a metal sphere which is placed on an insulated stand, then what will happen? If it is in contact with this, it will transfer its charge or some of its charge to this sphere. And when we remove it, then the charge will be evenly distributed on it. Now in this case, as the glass rod is in contact with the sphere, so this is charging by conduction. And we see here, glass rod has positive charge and it has given a part or entire, depending upon the size of this sphere, depending upon the time of contact, it has given a part of its charge to the sphere. And so charge on the sphere is also positive, similar to the charging body. Now let us consider charging by induction. In charging by induction, the glass rod which is positively charged, we have shown, it is placed close to a metal sphere. The metal sphere was initially uncharged. So when it is placed close to it, it's the side of the sphere which lies near to this glass rod acquires negative charge and the other side gets positive charge. And we have seen in our previous lecture that by earthing the positive side of the sphere and keeping the glass rods close to the negative side of the sphere, this metal sphere can acquire negative charge by earthing the positive charge. And when we remove the glass rod, then it will acquire negative charge which will be evenly distributed on it. Now what is the difference between the two? One, that this is conduction, so the glass rod has to be in contact with the metal sphere. In charging by induction, there is no physical contact between the metal sphere and the glass rod. The glass rod is placed close to it. Second difference is, in this case, the metal sphere has acquired the similar charge as that of the charging body. So positive charge glass rod has given positive charge to the sphere. On the other hand, if we look at it, look at the final diagram. So this positively charged glass rod, by induction, it has induced negative charge, opposite kind of charge on the metal sphere. Third point, which is very important, here there is sharing of charges. It means when glass rod charges this by conduction, it will lose some of its positive charge to the sphere. So there is decrease in its charge. On the other hand, in charging by induction, the glass rod which is used to induce charge on the metal sphere does not lose its charge. It will induce charge and it is not going to share its charge with that. I hope you have understood the differences between the charging by conduction and charging by induction. Now let us proceed. So here in this chapter, you will commonly heard this term, point charges. What do we mean by point charges? You should know. Suppose if we have charged bodies, as I have shown here, see two bodies I have shown, and here this is positively charged and that is also positively charged. If suppose the charged bodies in our discussion, its size is small, much smaller, the size of the bodies are much smaller compared to the distance between them. In that case, we can consider those charged bodies as point charges. It means point charges are the charged bodies which are having size much smaller than the distances between them. I hope it is clear to you now what are point charges. Okay, so now the next question that we are going to discuss is, what are the basic properties of charge? Now till 7th class, when you write those two basic properties, you can get marks. Hope you remember those properties. We have discussed them in the previous lecture also. There are two kinds of charges, positive and negative, and like charges repel each other while unlike charges attract each other. But if you write these properties in your 12th class answer, you will not be getting any marks for it. So let us consider the new 3 basic properties of charge which you are supposed to study in your 12th class. Okay. other than those two. First property is additivity of charge. First of all, you should know that charge is a physical quantity. Okay, it means it can be measured, and secondly, it has a unit also. And also it is a scalar quantity. It has only magnitude and no direction. So charge is a scalar quantity and it is a physical quantity. It has unit also. We know that there are two kinds of charges. So additivity of charge. In other words, charge is additive in nature. It means if you have any system which consists of many bodies, then the total charge of the system will be the algebraic sum of all the individual charges located at different points inside the system. Or here I'll read it. It means actually if in a system you have 10 bodies and they have all are charged, then what will be the total charge of the system? Charge, you have to take charge of each body. Let us say Q1, Q2, Q3, Q10. These are the charges of the 10 bodies. Generally, charge is represented by small q. So what will be the total charge small q? Q1 plus Q2 plus Q3 plus Q10. That will be the charge of the system. So the total charge of a system is the algebraic sum of all the individual charges located at different points inside the system. So here I have just shown if Q1, Q2, Qn are n point charges present in the system, then the total charge of the system Q will be Q1 plus Q2 plus so on, and we have to add all the charges, n point charges. Now this is just similar to mass. Mass is also additive in nature. Because in a system, total mass of the system is algebraic sum of all the individual masses present at different points inside the system. So this is similar to mass, but what is difference? Mass is always positive and charge can be positive or negative. Otherwise, what is similarity? That mass is scalar, charge is also scalar. Both are additive in nature, but mass is always positive, charge can be positive and negative. And we know that if a body's charge is 0 Coulomb, Coulomb I have not mentioned, we will be studying this later on in the next topics, that in one of the next topics that SI unit of charge is Coulomb. You must have heard this, you must have studied about this in your 10th class. In your 10th class, you have also seen one definition of Coulomb. So it's not new for you. So here I mean to say that if charge of the body is 0 Coulomb, it does not mean that there are no charges present inside it. It only means the total positive and the total negative charge, they are equal. And so Q1 plus Q2, the total charges is equal to 0 because the charges are balanced. Okay. So this is additivity of charge. I hope this property is clear to you. Now, the next property is conservation of charge. Conservation of charge means in an isolated system, the total charge always remain constant. Now, isolated is not a new term for you, as you must have done in your 10th class also. Isolated system means a system of maybe a large number of particles or bodies or charged bodies in this case, where there is no external force acting on the system. So a separate system. Here in an isolated system, the total charge always remain constant. In other words, we can say that charge is conserved in an isolated system. Or it means that charge can neither be created nor destroyed. It can only be transferred from one part of the system to another. Okay. So this is, you have, I think so you have started this this conservation of charge in your lower classes also. Okay. And also you have studied about conservation of energy, conservation of mass. Conservation of energy you have studied in physics, conservation of mass you have studied in chemistry. And whenever we discuss conservation, it is generally in an isolated system. Now, what is example for this? Yes, we can give an example for this. We have done the activity where we know that glass rod, when it is rubbed with silk cloth, both of them gets charged. Glass rod gets positive charge and silk cloth gets negative charge. Now, we know the cause of charging is transfer of electrons. And before rubbing both of them were neutral, so total charge was 0. And after rubbing, if glass rod, let us say, loses 5 electrons and gets minus q charge, then silk cloth will get those 5 electrons and will get, let us say, charge plus q. Silk cloth will get. So in short, when we rub glass rod with silk cloth, glass rod loses some electrons and the silk cloth gains those equal number of electrons. It means glass rod gets, let us say, plus q charge, and the charge on silk cloth that is developed is minus q. Both are equal and opposite. So when we take the algebraic sum, that will be again 0, which was the total charge before we rubbed them. So in the system of glass rod and silk cloth, the total charge remains constant, that is 0 coulomb. I hope you have understood conservation of charge here. Now the last basic property of charge is quantization of charge. That is, charge is quantized. What do we mean by it? See, when we rub glass rod and silk cloth together, what happens? Transfer of electrons takes place and ultimately resulting in glass rod losing electrons, gaining positive charge, and silk cloth gaining electrons and becoming negatively charged. Now in this case, the number of electrons transferred will be integral only, whole numbers only. Either it will be 2, 3, 4, 5, 10. Complete number of electrons will be gained or lost by the bodies. We cannot say that a fraction of an electron is transferred and the charging takes place. So this is the cause of quantization of charge, that during charging only integral number of electrons can be transferred. It means when 2 electrons are transferred from one body to the other, so what is the charge of 1 electron if we represent it by E? Then the body which gains electrons will get charge minus 2E, and the body which loses electrons will get the charge plus 2E. It means charge on the body can be 2E, 3E, 4E, 5E and so on. And it can be positive or negative depending whether it gains or loses. So electric charge is quantized. It means what? That electric charge is always an integral multiple of elementary charge E. We know that elementary charge E is what we know its value. We have used this in 10th class also. 1.6 into 10 raised to minus 19 coulomb. And this is a charge that an electron or proton carries. So in mathematical form, we can write the quantization of charge as this. Q is equal to Ne, where Q is a charge present on any body. N is an integer which can be 0, plus minus 1, plus minus 2 and so on. It has to be an integer. And E is the basic unit of charge, that is a charge carried by an electron or proton, because approximately we consider charges on them to be equal, but electron carries negative charge and proton carries positive charge. So I hope this is clear to you, okay, that charge on any body is always an integral multiple of this basic unit of charge E. Now, this quantization of charge was first suggested by Faraday, and then later on, after many years, this was experimentally proved by Millikan through his experiment. Okay? So just remember, because sometimes MCQ questions can come when you give any entrance, like who has suggested quantization of charge? Faraday. And who has actually demonstrated or proved this experimentally? Millikan. Okay? Now, you already know that the SI unit of charge is Coulomb. C-O-U-L-O-M-B. When you write the complete name, you have to start with small c, or if you write the symbol for the unit, you have to use a capital C. In your 10th class, how do we define Coulomb? We know this equation of electric current. Electric current is rate of flow of charge, or if you see this expression, I is Q upon T, where Q is the amount of charge that flows through the conductor or cross section of the conductor in time T. So Q upon T is amount of charge crossing the cross section of the conductor in unit time, and this is nothing but electric current. So from this expression, Q is equal to I into T, Q is 1 coulomb, when I is 1 ampere and T is 1 second. So from this we can define 1 coulomb is the charge that flows to the conductor when 1 ampere current flows to the conductor for 1 second. Hope you remembered this definition of Coulomb. We will study one more definition in this chapter. Now, let us see how big or how small this unit is. Okay. Now, to find how small or how big this unit is, let us try to find out number of electrons that will constitute 1 coulomb of charge. So, number of electrons in 1 coulomb of charge. For this, I'll use this equation, quantization of charge. Q is Ne. Q, I'll take it as 1 coulomb. N is the number of electrons and E is the charge on electron. I am not taking negative sign here. So E is 1.6 into 10 raised to minus 19 coulomb. So after I simplify, I get the value of N as 1 divided by this, and final answer is 6.25 into 10 raised to 8. Such a huge number. It means 1 coulomb, to give a charge of 1 coulomb, a body has to gain or lose, depending upon the sign, whether it is plus or minus, a body has to gain or lose so many electrons. It means this coulomb is a very, very big unit of charge. Because whenever rubbing takes place and the body gets charged, then the number of electrons transferred is actually very small compared to the total number of electrons present in the body. Okay, so since coulomb is a very big unit of charge, in the numericals you will commonly see the units used as millicoulomb or microcoulomb. These are the commonly used units for charge, and these are smaller units of charge. Millicoulomb. 1 millicoulomb, milli you know is 10 raised to minus 3 coulomb, and microcoulomb, 1 microcoulomb is 10 raised to minus 6 coulomb. I hope you have understood the 3 properties of charge: additivity of charge, conservation of charge, and quantization of charge. Now students, we know that like charges repel each other and unlike charges attract each other. It means that there exists this electrostatic force of attraction or repulsion between the charged bodies, depending upon whether the charged bodies have similar charges or opposite charges. Now let us see the law which gives the measurement of this electrostatic force between the 2 charges or charged bodies. Coulombs Law, named after the scientist Coulomb. Coulombs Law gives the measurement of this force. Let us see the statement. The force of attraction or repulsion between the 2 stationary point charges is 1. Directly proportional to the product of the magnitudes of the 2 charges, and 2. Inversely proportional to the square of the distance between them. This force acts along the line joining the 2 charges. I'll repeat it once again, and I hope you will remember some other law which is quite similar to this. The force of attraction or repulsion between 2 stationary point charges is directly proportional to the product of the magnitudes of the 2 charges and inversely proportional to the square of the distance between them. This force acts along the line joining the 2 charges. This law is just quite similar to the Newton's universal law of gravitation that gives us the measurement of gravitational force between 2 bodies due to their masses. Now this is the force between 2 bodies due to their charges, and gravitational force is a force between the 2 bodies due to their masses. Mass is of only one type, and so the gravitational force is always attractive in nature. There is no repulsion between the 2 bodies due to their masses. But on the other hand, this electrostatic force can be attractive or repulsive as charges are of 2 types. Charges can be positive or negative. So there is similarity and there are differences between the 2 laws. You should easily understand this law if you compare it with the gravitational law of Newton's universal law of gravitation. I hope it is clear to you. Let us put this in the mathematical form. So this is just the statement of Coulomb's law. Now in the mathematical form, we'll consider, I have not written here, I'll say it and you have to understand. Consider 2 point charges Q1 and Q2. So 2 point charges, remember we have to consider point charges. Consider 2 point charges Q1 and Q2 separated by distance r, and they are in vacuum. Vacuum is also called as free space, empty space. So Q1, Q2 are 2 point charges separated by distance r in vacuum. Then according to this Coulombs law, the gravitational force of attraction or it can be repulsion, because we have not mentioned what are their signs. So this electrostatic force. Electrostatic force can be attractive or repulsive, okay, because it depends on the signs of the two charges, okay. So this electrostatic force of attraction or repulsion, which we represented by F here, it will be proportional to product of the magnitudes of the two charges. So it will be proportional to Q1 into Q2. And it is inversely proportional to square of the distance between them. So the second point can be mathematically written like this. F is inversely proportional to square of r, where r is the distance between the 2 point charges. When we combine these two, then we get F is proportional to Q1 Q2 divided by r square. And when we put the equality sign, we get F is equal to K Q1 Q2 upon r square. So F is equal to, what is K? K is the constant of proportionality. And in vacuum, in SI unit, we have considered vacuum already, right? So this K in vacuum and in SI units, the formula for K is 1 upon 4 pi epsilon naught. So this is formula which is valid for vacuum. It can be in SI or CGS units, no problem. But the value in SI system or in SI units is this. K is 9 into 10 raised to 9 Newton meter square per Coulomb square. Okay, you have to, no need to by heart this, but if you by heart it's always good. But in the paper exams they always give this value. But you should try to remember this because it will be very commonly used in this chapter for numericals. So here I hope you have understood K is a constant of proportionality which is equal to 1 upon 4 pi epsilon naught. And in SI system or in SI units, value of K for vacuum is 9 into 10 raised to 9 Newton meter square per Coulomb square. Now what is 4 pi? That is constant. What is epsilon naught? Epsilon naught is called as permittivity of free space or permittivity of vacuum. Now this is a measure of how the medium allows the electrical influence to pass through it. It means it is a measurement of vacuum here, how it allows the electrical influence to pass through it. And if the medium is changed, then obviously we will not have this epsilon naught here because it will not be then permittivity of free space, then it should be permittivity of that medium. Suppose the medium is water, then instead of epsilon naught we'll have the permittivity of water. Okay, so here let us consider only stick to vacuum now. So K is 1 upon 4 pi epsilon naught. You should know its value in SI system and also the value of permittivity of free spaces, that is epsilon naught is 8.854 in 10 into 10 raised to minus 12 Coulomb square per Newton per meter square. Okay, so here I hope you have understood the statement of Coulombs law and you can also express Coulombs law in mathematical form. The thing is here this force acts along the line joining the two charges. See, I have represented here by force by this side. One force acting on Q1 is this side and force acting on Q2 is that side. In this diagram, obviously when I have shown the forces this way, it means I am showing repulsion. So this diagram can be considered when the two charges are like charges. If both are positive, then also there will be repulsion. If both are negative, then also there will be repulsion. Now let us see how can we define Coulomb by using Coulombs law. What is Coulomb now? SI unit of charge. Now take the Coulombs Law mathematical form. F is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R square. So we have considered the vacuum here. Now putting Q1 is equal to Q2 is 1 coulomb and R as 1 meter. We know the value of 1 upon 4 pi epsilon naught is 9 into 10 raised to 9 Newton meter square per coulomb square in SI system. So when we take magnitude of each charge to be 1 coulomb and distance between them as 1 meter, and after putting these values, the value of F can be calculated to be, and it is found to be 9 into 10 raised to 9 Newton. So from this we can define coulomb. 1 coulomb is the amount of charge, because we have taken here both the charges each equal to 1 coulomb. 1 coulomb is the amount of charge that repels an equal and similar charge. It means 1 coulomb charge only, with a force of 9 into 10 raised to 9 Newton when placed in vacuum at a distance of 1 meter from it. I hope you have understood. If instead of this, here we have taken similar charges, so both are plus 1 coulomb, let us say, or even if both are minus 1 coulomb, then also it will be repulsion only. If we take one charge to be 1 coulomb and the other charge to be minus 1 coulomb, then instead of repels, it will be attracts, and rest the definition will remain the same. Okay, and instead of similar, we get opposite. Instead of repulsion, attraction will be there. Instead of similar, opposite charge will be there. Okay, let me read this definition once again. 1 coulomb is the amount of charge that repels an equal and similar charge with a force of 9 into 10 raised to 9 Newton when placed in vacuum at a distance of 1 meter from it. Or we can also say 1 coulomb is the amount of charge that attracts an equal and opposite charge with a force of 9 into 10 raised to 9 newtons when placed in vacuum at a distance of 1 meter from it. I hope you have understood this definition of Coulomb. I hope the lecture is clear to you, and now you have learned the basic properties of charge, that is additivity of charge, conservation of charge and quantization of charge. You have understood what is Coulombs law. You can express it in mathematical form, and you can also define Coulomb from this law. So we'll continue with this chapter in our next lecture. I hope everything is clear. Thanks, students.